In the last video we looked at the measures of spread that you probably met at GCSE, and in this video we're going to introduce an important, very important measure of spread known as the variance, and a connected measure of spread known as the standard deviation. But to begin with, we're going to introduce something which was historically important but quite intuitive, and that's called the mean absolute deviation from the mean. So consider the data that we've got here, where we've got x taking the values 2, 3, 4, 5 and 6 with frequencies 1, 2, 8, 7 and 2. And we've illustrated it with a vertical line diagram. The mean of this data can be easily found on your calculator. It is 4.35. So the mean, if you like, represents the centre of the data. So I'll mark that in on the vertical line diagram. And a fairly intuitive measure of spread, which will take every single piece of data into account, is to calculate the average distance of the data away from the centre of the distribution, in other words, away from the mean. And this is called the mean absolute deviation from the mean. Now clearly, the smaller the value of this average distance, the closer the data will be to the mean. So the more closely packed the data is about the mean. We know the mean is 4.35, so when x equals 2, the distance of that data away from the mean is 2.35. Similarly, when x is 6, the distance of that data away from the mean is 1.65. And we can now add a column to our table showing the distance of each of the data values away from the mean. And having got this table, we can now calculate the mean of the d-values. And doing this on the calculator gives us a value of 0.785. And we get a mean distance of the data away from the mean of 0.785. It's worth noting that in the calculation of the mean absolute deviation from the mean, each piece of data that we have contributes to the calculation of this statistic. Historically, it was very much used in the early days of statistics. However, over the last 150 years or so, its importance has declined, since it is really quite difficult to establish the mathematical properties of this measure of spread. And this difficulty basically arises from the fact that the mathematical formula for evaluating d is rather complex. We can either write it as a two-part formula, d equals x minus x bar if x is bigger than the mean, but it equals x bar minus x if x is less than x bar, or it can be written as a rather messy formula involving both squares and square roots, that d is the square root of x minus x bar squared. The measures of spread that have taken over from the mean absolute deviation from the mean are called the variance and the standard deviation. These have slightly less obvious definitions than the mean absolute deviation from the mean, but have the advantage that they have very neat mathematical formulae, which then leads to the fact that they are easy to calculate using a calculator or computer, and equally importantly, their mathematical properties can be easily deduced with a modest amount of algebraic manipulation. So, if we take the square of the distance away from the mean, and let's call this now d star as an indicator of how far the piece of data is away from the centre of the data, and take the average of these values, then we will have a measure of spread which we can use in comparing different distributions. So let's have a look at calculating this. The measure of spread is called the variance of the data, and it can be calculated using the following steps. First of all, evaluate the mean of the data. Then, for each piece of data, work out d star, which is the square of x minus the mean for each piece of data, and then find the mean of the d star values. So let's have a look at this in terms of our particular example that we've been working with. We've seen that the mean is 4.35 already. The values of d star then, well, for the when x is 2, d star is going to be 2 minus 4.35 all squared, which is 5.5225. When x is 3, the value of d star is going to be 3 minus 4.35 all squared, which is 1.8225. And similarly, we've got the values for 4, 5, and 6. We can now find the mean of the d star values using our calculator. So the mean of the d star values is the sum of the d star values times f divided by the sum of the frequencies. Turns out to be 18.55 divided by 20, which is 0.9275. Now, really usefully, if we enter on our Casio FX991EX calculators the data in exactly the same way as we did in previous videos in order to work out the mean of the data, then we obtain the 3 output screens in exactly the same way as before. The value of the mean occurs at the top of the first output screen, and the value of the variance of this data also occurs on that first screen. Now, when we're doing statistics, often we are taking a sample from a much larger population in the hope that the sample will give us reliable estimates of the population statistics. Now, fortunately, mathematical theory, which is a little bit beyond the level of this particular course, tells us that the value of the sample mean gives us an unbiased estimate of the population mean. So we can use the value of the mean obtained from the sample as a good estimate of the population mean. Unfortunately, the value of the sample variance gives a biased, that is an unfair estimate of the population variance. However, the mathematical theory implies that only a small correction is needed to get a good, unbiased estimate of the population variance. And this corrected value is given by Sx squared, which is also shown on that first page of our calculator display. So Sx squared is an unbiased estimate of the variance of the population if the data came from a sample from this population. The measure of spread, called the variance, is calculated by these 3 steps, as we've seen already. Now let's have a think. Suppose the data is being measured in centimetres. Then the mean is also measured in centimetres. However, the value of d star is going to be a distance minus a distance, all squared. So the value of d star is going to be measured in centimetres squared. So the mean of the d star values, that is the variance, will also have units of centimetres squared. Now, in general, the unit of the variance is the square of the units of the data. So if the original data is in minutes, the units of the variance will be in minutes squared. If the units of the data is kilograms, then the units of the variance will be kilograms squared. Now, I find kilograms squared a really strange unit to have. and this can often be rather strange. So there's an obvious way around it. What we're going to do is we're going to take the square root of the variance to get a quantity known as the standard deviation, and this will have the same units as the original data. So we've got the standard deviation is the square root of the variance. So back to our calculator screen at the moment. We've already seen that the value of the mean is the first entry on the first screen. The value of the standard deviation of the data that we've inputted is that sigma x on that first screen. So in this particular case, the square root of 0.9275 is 0.96307. Now, as before, we said often a sample is taken from a population in the hope that the sample will give reliable estimates of the population statistics. Mathematical theory tells us the value of the sample mean gives us an unbiased estimate of the population mean. We've already said that. Mathematical theory tells us as well that only a small correction to the sample standard deviation is needed to get a reliable estimate of the population standard deviation. And this corrected value is given by Sx. And Sx is simply the square root of s squared x. So in this case we've got an estimate of Sx, which is 0.9881. For group data we use the mid-mark to find the mean, and we again use the mid-mark when we're calculating the variance and the standard deviation for a set of data. So what I'd like you to do at this stage is just pause the video and use your calculator to calculate the mean, variance and standard deviations of the times taken by these 25 pupils to complete a 5-kilometre cross-country course. When you've done that, start the video again. And use the values that you've just calculated to deduce estimates of the mean, variance and standard deviation of the times that all 15-year-old pupils would take to complete the same cross-country run. Having used our calculator now to find mean, variance and standard deviation, let's make sure we've got the formulae for variance and standard deviation established as well. The process for finding the variance has been described already and can now be expressed as a formula. We can say that the variance is the sum average of the d stars, so that is the sum of the d stars times the frequencies divided by n, or if you like, the sum of the d stars times the frequencies divided by the sum of the frequencies. Since d star is x minus x bar all squared, we can now write the variance is the sum of the x minus x bars all squared times the corresponding frequencies divided by the sum of the frequencies, or the sum of the x minus x bar squared times the frequencies divided by n, where n is the sum of the frequencies. It can be shown that this formula can also be rewritten as the sum of the x squared f's divided by the sum of the f's divided minus x bar squared, or the sum of the x squared f's divided by n minus x bar squared. And we can now write down the subsequent formulae for the standard deviation, since the standard deviation is simply the square root of the variance, and we have these different formulations for the standard deviation. It is useful to have an interpretation of standard deviation, and I find the result that states that most, by which I mean at least 3/4, and often in fact more than 95% of any frequency distribution will lie between the mean minus 2 standard deviations and the mean plus 2 standard deviations. And we shall call this the 2 standard deviation rule. And it will be a good idea at this stage just to check that the 2 standard deviation rule works for the example that we've just looked at. That was the times of the cross-country runners. Finally, we consider the choice of which measures of central tendency and spread should be used. Our first choice should be the mean for the measure of central tendency and the variance and standard deviation for the measures of spread, since each piece of data contributes to the evaluation of these statistics. The mathematical properties of these statistics are relatively easy to obtain, and most importantly allow estimates of population statistics to be made from knowledge of the statistics gained from samples drawn from the population. The disadvantage of these statistics is that outliers in the distribution can have a marked effect on the value of the statistics. Our second choice should be the median and the interquartile range, which has the advantage that outliers have little, if any, effect on these statistics, and that box and whisker plots, together with the plot of the outliers, give good visual comparisons between distributions. However, the mathematical properties of these statistics are much more complex, and this makes it difficult to make estimates of the population statistics from knowledge of the corresponding statistics of a sample drawn from the population.